In the beginning, there was darkness, and then, bang, giving birth to an endless expanding existence of time, space, and matter. Now see further than we've ever imagined, beyond the limits of our existence, in a place we call the universe.
It is both mighty and meek. Humanity's quest is to harness its power and escape its bonds.
Holy cow! This is what an astronaut feels.
It creates and breaks the stars, the planets, the galaxies, and directs their cosmic roller coaster ride.
Gravity's our friend and our foe.
Without it, life as we know it would end.
The Earth would literally explode.
It is the magnificent and mystifying force that rules the universe. Gravity. Gravity is the most pervasive force in the universe. It is at work on massive and minute scales, on the routine and the extreme. A surfer needs it to hang 10.
When you ride a wave, you're going to slide down the front, and you're going to use that pull of gravity to get you going. It's your acceleration force. It's your accelerator. Gravity's your accelerator.
A skier uses it to race downhill. A snowboarder must have it to get big air. It acts on everything with mass, including us, 24/7, even when sleeping or standing.
Gravity here on Earth, of course, is always accelerating us down toward the center of the Earth at 32 feet per second squared.
At a theme park, gravity is the galactic gas that makes roller coasters roar and people scream.
The gravity of the Earth pulls us down, and that's going to make us go really, really fast.
All objects with mass or energy, particles, people, planets, stars, and galaxies produce gravity. Omnipotent and omnipresent, gravity attracts, governs, warps, shapes, makes, and takes all matter and mass in the universe.
So it's pervasive. It acts on all things through extremely large distances, and nothing escapes its pull.
It is gravity that holds our solar system together.
The force of gravity is basically the thing that holds us on the planet, keeps us from flying off.
It is the cosmic glue that binds all matter in the universe together.
If you were to imagine taking two dice and putting them perfectly at rest out in the middle of space and separating them by a centimeter, then what you'd see is that over the course of an hour or so, those two dice would slowly come together and touch.
Gravity made our world.
Our sun formed from a vast cloud of gas that gravitationally contracted. Similarly, our Earth formed through the gravitational attraction of little particles, little bitty things, gradually growing into a bigger and bigger object.
When it comes to gravity's pulling power, mass and distance matter.
It depends on the masses of each object, the amount of matter within each object. So it's proportional to the product of the two masses.
In other words, the bigger it is, the harder it pulls on other objects. But that's not all.
And it's inversely proportional to the square of the distance between them.
This means if you double the distance between two objects, the attraction or pull is only a quarter of its original strength. The pulling power of gravity lets it direct the motion and movement of all matter, however massive, in the universe.
So you have whole galaxies, for example, in orbit around each other. Clusters of galaxies all orbit around their common center of mass.
But it is the practical potential of harnessing this relentless force that has obsessed scientists for centuries. It would literally fall to Galileo Galilei, the 17th century truth seeker, to first recognize that gravity even existed.
Galileo found that objects having a different weight fall at the same rate. So here's a very heavy steel ball and a light ping pong ball of the same size. And if I drop them at the same time, they hit the ground at exactly the same time as well, because they fall at the same rate.
To illustrate Galileo's most profound gravitational discovery, that all objects, regardless of mass, fall at the same rate, we take a ride on the mega-fast super manly escape at Six Flags Magic Mountain in Southern California. The theme park ride is the stage for a spectacular free-fall demonstration. It will show what happens when a car full of people and a tennis ball fall from 415 feet in the air.
Okay, here we go.
All right. Oh, bye.
The riders are shot up the 41-story tall tower at 100 miles an hour. With their eyes open, gravity will help them see a superhero.
Oh my God! Okay, I'm gonna drop this ball now, and oh my God, it's floating around. It's floating. It's floating. It's floating. Oh, the wind blew the ball away that time.
While we expect all objects to fall freely together, regardless of mass, on a windy day, results aren't always perfect.
All right. Oh my God.
At the very top of the ride, when upward motion has stopped, gravity takes over, and the downward freefall begins.
Oh God, I'm gonna drop this ball, and it's gonna float. It's gonna float. Oh, it's floating. It's floating out. Oh.
And then, for a few blissful seconds, theme park thrill seekers feel weightless, as if they are free of gravity, or in what scientists call zero G.
Oh, that one floated well. That one floated well.
Oh man. Oh. Oh. I'm gonna try dropping the ball. Oh. Okay.
But zero G is just an illusion. In reality, gravity is running this ride. It's the force that yanks the car, the people, and the tennis ball, indifferent to their mass, back down to Earth at the same rate.
Oh, that's a fantastic ride. I mean, feeling oneself drop is amazing. But what's really great is dropping the ball and seeing it floating above my face. Now, I mean, it's falling. I know it's falling, but I'm falling at exactly the same rate. It doesn't matter how massive something is. It falls under the force of gravity at exactly the same rate.
Thanks to experiments like this, we now know that objects all fall at the same rate. But what would it take to launch a cannonball into orbit? When the famous British physicist Sir Isaac Newton saw the apple fall, that some say hit him on the head, it changed the world.
You got the apple falling from the tree, and he looks up and sees the moon in orbit around the Earth, and judges that not only is the apple falling to Earth, so too is the moon.
But could the moon really be falling? By thinking of a cannon and the trajectory of the ball it shoots, Newton used math to unlock a cosmic mystery. It came in his landmark publication, Principia Mathematica, in 1687.
Isaac Newton has a famous drawing, and in it he draws a planet and a little mountain. And there's a little projectile first kicked off the mountain, and it falls down a little bit. You give it more speed, it goes a little farther out.
Now say you could just increase the force all you wanted. It could go 50 miles, it could go 100 miles before it fell.
By adding more gunpowder, and with just the right angle of fire, a cannonball can be made to go faster and farther. Inevitably, however, gravity wins, pulling the cannonball back down to Earth.
The Earth is round and not flat, so Newton realized that if the cannonball is fired at sufficient speed, the cannonball would actually go into orbit.
For that to happen, Newton determined, the ball would need to be shot out of the cannon at 17,500 miles an hour.
It starts curving around the Earth, and he realized that there must be a speed where it goes completely around the Earth and hits you in the back of the head, never actually hitting Earth's surface. And if you duck, it'll just keep going, and lo and behold, you have an orbit.
But why doesn't the moon fall to Earth?
The moon also has some sideways motion. So for every little bit that it falls down, it also moves off in this direction, and the sum of all those motions is an orbit around the Earth.
Newton also realized that the Earth is in a giant freefall around the sun. With gravity forging the path, our planet rounds the sun like an endless cosmic roller coaster ride. Newton cracked the gravity code, and physicists are still using his ideas to solve all sorts of problems. Some of them stranger than others, like what would happen if a person tried to travel through a tunnel from one side of the planet to the other? In this wild scheme, you'd have to drive a straight-line tunnel right through the Earth and use gravity alone to propel a traveler down this so-called gravity express.
So suppose you've got one of these tunnels, and you jump in. Initially, the Earth is pulling down. You're going toward the center of the Earth, and so you're accelerating toward it. But as you pass through the center of the Earth and start going out toward the opposite side, the gravity of the Earth is trying to pull you back, so it's decelerating you.
So gravities actually have a braking effect. There's no fear of shooting out the hole on the other side of the Earth at some tremendous velocity and shooting yourself back into space. But in fact, you reach the surface of the Earth exactly. You will coast to a perfect rest. In 42 minutes, you'll be there.
Whichever two cities you connect with a straight-line tunnel, it takes gravity exactly 42 minutes to get you there.
The journey from Los Angeles to Paris, 42 minutes. Suppose you wanted to go from Los Angeles to Tokyo, 42 minutes. It doesn't matter which path you take through the Earth. The journey is always 42 minutes long.
It takes Newton's math to figure out why this works.
If we connect Los Angeles to New York, taking a tunnel, obviously the tunnel would not go straight down, but it has to go down at an angle.
The angle slows the speed of descent.
But the distance is also less, and if you work out the equations, lo and behold, the two effects cancel, and you still get there in 42 minutes.
It takes 42 minutes regardless of the path you take. That's really cool.
Newton figured out what gravity does, but it took the brilliance of physicist Albert Einstein to work out why it was doing it. Einstein realized that gravity is really caused by huge objects like stars and planets literally bending space itself. Like a massive rubber sheet space is curved when massive objects sit in it. In fact, Einstein proposed that the path planets take around their stars, their orbits, are all a direct result of this curvature of space.
He said that what an orbit is really something traveling in a straight line. When something is free-falling towards another object, it really is just traveling in a straight line through space-time. However, the curvature of space-time bends its path into a closed orbit, but space itself curves it back in on itself.
This revolutionary discovery came when Einstein, in the early 1910s, realized that orbits of stars and planets in the observable cosmos behave just as Newton's math predicted, except one, Mercury. Its orbit essentially wobbles.
Einstein described gravity as a curvature in space and time. And the orbit of Mercury works perfectly when you take that into account. Mercury isn't moving in flat space, but curved space around the sun. Then the orbit's perfect.
This curvature of space is at play in our own solar system.
Earth is simply following what it thinks is a straight line path, the shortest distance between 2 points, in this intrinsically curved space.
Einstein not only determined that mass warps space, it warps time too.
So henceforth, Einstein proclaimed, physicists should not speak of space and time separately, but of space-time as one unified object.
While it's uncomfortable to many the first time you hear it, if you stop and think about it, it's actually quite obvious. If I'm going to make an appointment with somebody, I don't say, I'll meet you at 3 o'clock. That's not enough information. There's got to be a question that follows that. What is that question? Where? If I say, meet you in room 203, when? Anytime you intersect with someone else's life, you do so at a time and at a place.
Einstein's realization that space is curved and that time and space are in fact intertwined is now the very definition of gravity.
Liftoff of the Space Shuttle Discovery.
Unlocking the secrets of gravity has enabled humanity to escape our earthly shackles and open the universe for exploration. But how can future astronauts on the long way to Mars survive the disabling effects caused by zero-G? Gravity is our friend and our foe. It is the fearsome force that propels a skier and the snowboarder down the mountain and shoots them into the air. With enough momentum, an airborne snowboarder can feel, for fleeting moments, as if they are free of Earth's gravitational pull.
You're actually weightless when you go off the jump. The period of weightlessness is determined by the duration of your trajectory is a function of your velocity. So that the snowboarder who gets really good big air may achieve a second, 2 seconds, even 3 seconds of weightlessness.
But in the end, gravity wins. And the high-flying, free-falling boarder, just like the ball fired from the cannon, is eventually yanked back down to Earth.
It's free fall for the snowboarder as he or she goes over the jump and creates this trajectory. It's just as much free fall as a cannonball going through the air. And the trajectory is determined only by the velocity and the force of gravity. Then, of course, what happens on the landing is another story.
But what if a snowboarder aspired to reach even greater heights? What if he wanted to overcome gravity and launch himself right off the planet?
You want to leave Earth entirely and forever? Earth has what we call the escape velocity, this magic speed where if you pass that speed, you will escape Earth forever, never to return.
Escape velocity, the minimum speed any object needs to reach in order to escape from the Earth, is about 7 miles a second. That's 25,000 miles an hour. In theory, even a snowboarder with enough momentum and aimed in the right direction can take off just like a rocket. Escaping Earth's gravity may not be realistic for a snowboarder, but it has proven possible to launch people and projectiles into orbit.
You can leave systems, you just need enough energy to do so. And we've garnered enough energy and technological know-how to do just that in our voyages to the moon. And our hope that that will continue on to Mars and beyond.
To get to Mars and beyond, mankind will have to harness gravity's energy. Just like we always do when we're seeking thrills to the extreme. Gravity gives us two types of energy: potential and kinetic. Potential is just that. It's energy that's being stored, while kinetic is the result of all that pent-up potential energy. This fantastic phenomenon works on a roller coaster.
As you're winched up on a hill, your potential energy is increasing. You literally have more energy at the top of the roller coaster than at the bottom. It's not just a weird abstract thing. You actually possess higher energy at the top. And that's turned into speed, into kinetic energy, as you go down that hill on the roller coaster.
I'll be converting my potential energy to kinetic energy! Woo!
When a surfer hits that sweet spot on a wave, they're using energy's double act. NASA also uses this energy exchange principle to add some speed to their missions. As a spacecraft nears the orbit of a planet, it too gathers kinetic energy at the expense of potential energy. Then, as it rounds the planet on its cosmic coaster ride, the craft gets a slingshot effect that punches it onward with more kinetic energy.
When the Voyager spacecraft visited Jupiter in 1979, 1980, it flew past Jupiter, and Jupiter tugged on it, giving it extra motion, sort of a slingshot effect. Not only changing its direction of motion so that it was aimed towards Saturn, but also speeding it up.
Knowing how to use the power of gravity will enable humanity to travel further and faster across the universe. Having the physics formulated and the technology available is just one part of the preparation for extraterrestrial travel. Readying people for the rigors of space is the other. Far away from Earth's gravitational pull, in a spaceship on the long journey to Mars, for example, future astronauts will have to learn to live, work, and play in an environment free of Earth's sizable gravity. One where they effectively feel weightless and all objects move equally and freely. One fun way to experience the astronautical thrills and spills of space travel is to simulate it on a zero-G flight.
I'm really looking forward to this. This is going to be an incredible experience.
By riding the ultimate roller coaster, a specially modified zero-G Boeing 727 aircraft, astrophysicist ḻģᴇᴏ<hesitation> is about to go on the ride of his life.
It's going to be like a ball thrown up in the air. Weightless, because it will be in free fall. So I'll be floating around as though there's no ground holding me up.
The zero-G flight flies between 24,000 and 32,000 feet. This is about the same altitude as a regular commercial jet. But that is where the similarity ends.
The water's the next one.
The path it follows is a series of coaster-like rolling hills in the stratosphere. Just like Superman the Ride, the Super Zero-G plane gathers potential energy as it climbs up at 45 degrees. Passengers feel this as an increase in weight. Gravity is measured in terms of G-forces. 1 G is the amount of gravity we feel standing on the surface of the Earth.
I'm gonna get back down like this and get ready.
As the plane steeply climbs, accelerating upward, the gravity G count rises and people feel heavier.
All right. Oh,
The plane is accelerating us upwards at about 1.8 G at its maximum.
As the flight approaches, then eases around the apex of the arc, the plane, as well as all the people inside it, are in effect in free fall.
0 G coming up. Oh, man. What an indescribable feeling. Holy cow. Oh, I'm out in free space. Falling, just floating. This is what an astronaut feels.
The plane's trajectory induces weightlessness again and again by flying a series of these parabolic arcs. Even though they are within the cabin of a plane, the 0 G passengers are freely falling towards the Earth, just like skydivers. But what creates the sensation of weightlessness? It goes back to Galileo, who showed that all objects fall at the same rate. So as the plane and the people inside fall freely toward Earth, they maintain the same position relative to each other. And that is why they feel weightless.
The feeling lasted 25 full seconds because for 25 seconds we were essentially in free fall. It was like Superman just flying through the air. Oh, I cannot believe how it feels.
When the jet's engines re-engage and end the free fall, the passengers feel their weight return. As Einstein would say, weightlessness is but an illusion.
This is so awesome! So awesome!
The 0 G plane takes advantage of something Einstein worked out back in 1916 in his general theory of relativity, that acceleration is essentially the same as gravity. When you are thrust upward in a rocket or the 0 G plane, the G-forces you experience are the same as you would feel being tugged downward by the gravity of a massive object, like a planet. So gravity and acceleration create the same sensation. That's how the passengers on a 0 G flight can feel like an astronaut and can experience the joys of weightlessness.
Natural path through curved space-time. This is what Einstein's theory says, independent of the mass. We all follow the same path. Oh yeah, this is unbelievable.
On the 20-minute, 15 parabola flight, there's time in between the frights and delights to further taunt the laws of gravity.
Okay, here we go. Oh, man.
As well as entertaining weekend warriors, the parabolic flights, also inauspiciously called the Vomit Comet, have a practical purpose. They prepare NASA astronauts for working and living in the 0 G environment of space. With these sensational parabolic flights, humans have learned how to simulate the absence of gravity. But is it also possible to create artificial gravity in the lab?
These experiments will lead to a successful exploration of Mars. It is in our future.
At the dawn of the 21st century, overcoming the bonds of gravity and escaping Earth's sizable tug have been realized. The next step is to design and build the technology that will allow humans to travel, work, and live on exotic alien planets.
And we've garnered enough engineering know-how to do just that in our voyages to the moon.
Thanks to state-of-the-art technology, humanity is on the brink of a new era in space exploration.
The trip to Mars is beginning here at our laboratory at MIT. Artificial gravity may be one of the ways that we overcome the debilitating effects of weightlessness.
Since the advent of the space age, scientists have been concerned with minimizing the life-threatening risks and damaging effects of being weightless at 0G.
The issues originally had to do with human survivability. We didn't even know, back in the Apollo period, how people would react to stays in space of more than a few hours. There was all kinds of concern about humans' ability to control a vehicle after being exposed to weightlessness for a long period of time.
A mission to Mars would require astronauts to be away from Earth's gravity for at least 2, maybe 3 years. The human frame is simply not designed for the absence of terrestrial 1G gravity.
The architecture of our bodies is designed to withstand our weight under the forces of gravity. Gravity determines how our cardiovascular system reacts. So when you get out of bed and you go from being supine to upright, there's a regulatory system that keeps the blood pressure reacting against the forces of gravity.
Experience has shown that being weightless for long periods leads to bone loss, muscle deterioration, and life-threatening blood clots. Aeronautical engineers at NASA and MIT are testing a personal centrifuge system that may mitigate the very real dangers.
They protect their heart, their bones, their muscles, and even in these early experiments, we have every reason to believe that artificial gravity with short radius centrifuges may be the universal antidote that we're looking for to protect people on the long trip to Mars.
Just like a theme park ride, spinning a subject artificially creates G-forces. To prevent motion sickness in the MIT ride, astronauts are conditioned to keep their heads still. By spinning a person at 30 revolutions a minute, the centrifuge imparts 1G, the same force felt pulling down a person standing on Earth. Scientists hope that one day a trip to Mars will be a reality. On board, they believe there should be a personal centrifuge. To get their earthly gravity fill-up, 21st century astronauts could then just spend 1 hour a day on the machine.
We get onto it for a brief period every day and get spun up quite fast. Spun up in what I'll call a spin in the gym. You go for your exercise, you go for your workout, you get your G tonic, your gravity tonic.
While a trip to Mars may still be decades away, astrophysicist and seasoned skier Լᴇᴏ can dream of big air and the liberating gravity of Mars. On the surface, there is 3/8 the tug of Earth's gravity.
Everybody likes to get some air. Everybody likes a little, but just think if we were on Mars.
A person who weighs 100 pounds on Earth would feel as if they weigh 38 pounds on Mars. Although a Martian skier would fly down Olympus Mons at 1/3 of the speed they would on Earth, the lower gravity also means they could get at least 3 times the big air.
In the case of gravity, it's mass that matters. The more mass you have, the stronger the pull of gravity. So when you think about what your weight would be on the Earth versus something more massive than the Earth, it's pretty direct. If something were twice as massive as the Earth, you'd weigh about twice as much.
The big kahuna in our solar system is Jupiter. On that planet, a 100-pound person would weigh a whopping 254 pounds. Even if Jupiter had a solid surface, a skier there would have to fight for big air. What we already know about gravity, how it works and how it can be used for practical purposes, could, in theory, even save the planet from its ultimate cataclysmic fate. Here's how gravity can come to our rescue. Gradually, in about 5 billion years, our sun will brilliantly flare, turn into a red giant, gloriously burn up, and die. As this comes to pass, our inner solar system is engulfed, and Earth's gravity and atmosphere will be radically altered. At that point, life on the blue planet will end. But astrophysicist дэлʀᴇᴏജ has a plan to use gravity to save Earth.
This environment that we have here now would look very similar to the environment that is holding sway on Venus right now. A crushing carbon dioxide atmosphere, temperatures hot enough to melt lead.
But rest assured, if the worst hypothetical happens, gravitational science could save Mother Earth.
The one thing that we could do over the very long term is to somehow move the Earth's orbit out to a larger distance from the sun where the temperature isn't so high. And a way that you can do that, if you have enough time, if you have billions of years available to you, is to use a comet or an asteroid.
This mega move would require astronauts and engineers aboard a spacecraft to maneuver the comet or asteroid just in front of the Earth.
In order to be most effective, the comet has to fly very close to the Earth, within orbital radius or so of the Earth.
Then, on the cosmic roller coaster, potential and kinetic energy are roused, and gravity does the rest.
If that happens, then the comet pulls the Earth forward, the Earth pulls the comet backward, and the net result is that the Earth is given a boost. It's given a boost to a slightly higher orbital radius, slightly larger distance from the sun. And if you make one of these adjustments, one of these passages every 10,000 years or so, then the Earth, over a period of 1 billion years, can move at a fast enough pace outward to keep track with the steadily brightening sun.
If, however, the experts get the math wrong and the big gamble doesn't work, all bets are off.
And if you screw that up, then you can have a collision between the comet and the Earth. So a 100-kilometer object crashing into the Earth is absolutely an extraordinary disaster. It's the kind of thing that causes huge extinctions of gigantic numbers of species.
Of course, this is only an extreme hypothetical scenario. But what is known for sure is that our continued existence today here on Earth is contingent on the presence of gravity. It allows for the perfect conditions for life and the pursuit of happiness. 1G produces the surfer's dream, a perfect wave. But the wild waters enjoyed on Earth are not the only kind of gravity-generated waves. There are cosmic waves so large, they roll across the entire universe. Tidal torrents of gravity-boosted particles roll across the cosmos. According to Einstein, these gravitational waves wash through the universe. But what are they?
Any change in the gravity sends a ripple through that fabric of space that moves at the speed of light. That would be a gravity wave.
And why do they happen?
If you have two objects, two compact stars, each of which curves space around them, and they're orbiting one another, then the result is that these two curved regions create a wave, a ripple in the structure, in the shape of space that moves outwards, carrying energy with it. That's called a gravitational wave.
I mean, literally, you can think about space and time having a wave, just like an ocean wave in it, that travels through the universe. Gravity waves are just the same.
Any type of mass in motion, big or small, generates a gravitational wave. And like the Earth's ocean tides, gravitational waves roll ceaselessly across the cosmos. In theory, a surfer launched into space could experience an out-of-this-world wipeout and warp.
If a gravitational wave was created in space or somewhere and went through you, what would happen is you'd get fat and then you'd get skinny, meaning that space was distorted. Space in one direction made you fatter, in the other direction it squashed you, and it goes back and forth.
But for Earth-bound scientists to detect any faint G-wave signals, the disturbance needs to be propagated by a massive cosmic object. Black holes and spinning neutron stars can do it.
Another thing that can make a gravity wave is an explosion. Say a supernova, a star explodes and it goes whack. And that actually pushes a gravity wave forward.
The tool to catch the light-like signal from a wave is the LIGO, the Laser Interferometer Gravitational Wave Observatory. There are two identical ground-based LIGO labs. One is in Hanford, Washington, and the other is more than 2,000 miles away near Baton Rouge, Louisiana. If a wave comes by, each lab's results will be vital to confirm the event. Here's how it works. Super polished glass mirrors are at the fulcrum of the interferometer, which is a tool that basically compares two light wave measurements and identifies the differences between them. Precision laser light is fired back and forth and split between two calibrated mirrors. In normal circumstances, as the light bounces up and down the 2.5-mile-long L-shaped vacuum tubes, the two laser beams are basically in sync. This means the beams effectively cancel each other out, and no light escapes the tunnel. But when a gravity wave rolls through, space is ever so slightly stretched or squashed. As a result, the laser beams are thrown out of phase, and only then a small amount of light is emitted. A tiny signal, less than the diameter of a human hair, 1/1000th the size of a proton, will register. Converted into a sound and a light signal, it will be seen and heard. The scientists' greatest hope is to catch the most massive event that ever occurred in the universe, the Big Bang.
Gravity waves may be our best chance to look very, very close to the beginning of the universe. About 300,000 years after the Big Bang, the universe was so dense, it was actually opaque to light. Light could not travel through it. So if light can't travel through the universe, what can? A gravity wave.
The problem is, a minuscule signal from a gravity wave has yet to be caught.
It's clearly hard. In fact, when Einstein predicted them, he thought it was a nice idea, but no one would ever be able to detect them. It's only the advances of technology that give us a chance.
LIGO scientists, like astrosurfers, live for the day when they can hang 10 and ride their very own perfect wave of gravity.
We've seen what we think are the effects of gravity waves, the loss of energy from a system by way of gravity waves, but we never directly detected one. That's one of the last frontiers.
If the LIGO scientists' quest is successful and they catch a wave, it could change science.
So I think the long term is first to understand gravity, and then even more interestingly, to understand the universe.
The force of gravity has domain over our universe. It created and can destroy the cosmos, the stars, the planets, and the people. It controls our lives, our play, and our endeavors.
And therein is this cosmic ballet.
Our collective future depends on the grace and greatness of the mighty ruler of the cosmos, gravity.